Hello, in this video we're going to go over the theory parts of Lab 1 and CPAC 210L, which is about logic gates. We're going to start with introducing the basic logic gates and then move on to simulation through the software Logisim. Basically, logic gates are the basic building block in a combinational digital logic circuit. There are three basic logic gates that includes the AND gate, the OR gate, and the NOT gate. For every digital logic gate, we have to have logic inputs, meaning inputs of values zeros or ones. Alternatively, we can say logical low or logical high. So L means 0, H means 1. For the gates, we have one singular output, and the output could have a value of 0 or 1. So think of these as operations between digital bits or binary bits. Let's start with the AND gate first. On the right side, you see the symbol for the AND gate or the two-input AND gate. You could have an AND gate that has more than two inputs, but you can only have one output for the AND gate. And the output is defined for the AND gate as 1 only if all the inputs are 1. If any of the inputs is 0, then the output is automatically 0. So the condition for having an output equals to 1 at the output is to have all the inputs equal to 1. Here we have labeled the inputs as A and B, the output as Y, and only if A and B, which is the last row in the table, only if A and B are 1, then the output is 1. We can express the AND gate as a circuit diagram through the symbol, or as a mathematical or actually a Boolean expression, such as Y is equal to A and B. You can spell out the word AND, or you can simplify it using Boolean algebra by removing the word AND. In math, this is equivalent to multiplication, but in Boolean algebra, this is called ANDing. So Y is equal to A and B. This is how you read it in digital logic. What we see on the left is called a truth table. So a truth table basically represents all the possible input combinations and their corresponding output for a digital combinational circuit. For a two-input circuit, we have 4 possible cases: 0, 0, 0, 1, 1, 0, and finally 1, 1, and their corresponding output. So this is the complete truth table for a two-input AND gate. Next, we have the OR gate. You can see here the symbol for the two-input OR gate. If you want to have a 3-input OR gate or a 4-input OR gate, the symbol looks the same, except you will add more lines at the input. So the input here is A and B, or the inputs are A and B, and the output is Y. The OR gate states that, or has the condition of, we can say the OR gate outputs 1 when at least one of the inputs is 1. When all of the inputs are 1, this is perfect. We're going to output 1. When only one of the inputs is 1, we're going to output 1. If we have a 4-input OR gate and only 3 of the inputs are 1, then the output is 1. We can alternatively say that you will output 0 only when all the inputs are 0. Otherwise, you will output a 1. Okay? We can write this as an expression or a Boolean expression as Y is equal to A and then spell out the word OR and then B. Or you can use the symbol, the addition symbol in math to represent ORing. So the last line here is, or the last expression is actually Y is equal to A or B. You don't read this as A plus B, but rather Y is equal to A or B. Okay? And remember, the condition for having a 1 at the output for the OR gate is to have at least 1, 1 at the inputs. The last gate we're going to cover in this video is the NOT gate. The NOT gate, or the inverter, another name for it, only takes one input. There's never a two-input or inverter. It's just one input inverter, and it has one output. The output is the inverse of the input. If you give it a 0, it will output 1. If you give it a 1, it will output 0. So this is the complete truth table of the inverter gate or the NOT gate, and it has only 2 rows because we only have 1 input, and only 2 possible cases are possible. That input could have a value of 0 or 1. And we can express it as y is equal to not a, or y is equal to a bar. Another way to write it, which is also common, is to say y is equal to a bar. This is equivalent, so we can say not a not, a bar. Okay, these are all representing the NOT gate. If you notice, at the end of the NOT gate there is a circle. This will be useful in future labs to remember that the circle at the end of the inverter means inverting. Without the circle, this is actually called a buffer. So the triangle by itself is a buffer, but it's outside the scope of the lab. We can represent a digital signal through what's called a timing diagram. Okay. The timing diagram can be useful if you want to look at or visualize the signal throughout time, as it's changing throughout time. So rather than seeing the instantaneous value of a signal, you can sketch it as it's changing over time. This comes in handy in future labs, but I'm still going to introduce it now. So here what we have is a singular signal whose value is varying through time. It starts at 1 at the beginning, so here it's a 1. Then at some point it changes to 0, and then it changes back to 1, and then finally it resets to 0. So this is another way to represent a digital logic signal through a timing diagram. You can just sketch it as a line. If the line is high, it's a logic 1 or logic high. If the line is low, then that's a low signal or logic 0. In this slide here, you see a screenshot of the software Logisim that we'll be using. You can take a screenshot of this because it just shows you how to navigate through Logisim, what each button represents, and so on. But in the next video, there is a detailed tutorial on how to simulate the 3 logic gates using Logisim. I'll briefly explain what you see here. So the window of Logisim is very straightforward, very simple. In here you have the button that will allow you to control the values of the inputs. You can assign a 0 to the input or a 1, and all of the controlling can be done after clicking on the hand here. If you're in the editing mode of the connection or the circuit itself or the design, you will click on the cursor. So you will navigate or switch between the cursor and the hand. The cursor will allow you to edit the circuit. The hand will allow you to edit the value of the inputs, the input pins. This brings us to the input pin. The square here is an input pin. You can use it for the input of the gates or the circuit, the digital circuit that you have. The circular pin is considered an output pin. It will indicate to you the value of the output of a circuit. So the output pin you will read from, you will use it to read the value of the output. The input, you will use it to feed in inputs to your digital logic circuit. And here we have the three basic logic gates that we introduced: the NOT gate, the AND gate, and the OR gate. All of them are listed here. For more gates, we're going to expand the gates, but we're going to need that later on. But for the purpose of the first lab, it's enough to use the toolbar at the top. Here, for the gates themselves, if you want to place them directly from here, even if you want to place them from here, they by default come with a specific number of inputs. The inverter only comes with 1 input. The AND gate by default comes with 5 inputs. So once you place a gate, or even later on, if you want to adjust the settings of a gate or the options of a component in Logisim, make sure to click on the cursor first, and then click on the gate on the board here, for example, and then on the bottom left side of the screen, you should see all the settings regarding the component that you're selecting. Okay, one of the settings for the AND gate, for example, will be the number of inputs. You can control the number of inputs through there. Okay, and another important thing that is very important and maybe easy to miss or to not find is the zoom button here. In order to zoom, you have to click the upper cursor here. To zoom out, you will click on the bottom cursor. Okay, so this is basically it for lesson. If you have a question, you can leave it in the comment or ask me during the live lab session or send me an email if you're my student.